Hey everyone. So where we left off, we talked a little bit about just the overview of database design and some vernacular we'll be using throughout the semester with it. We're also going to be looking at this idea of a general structure of a database, and then later we're going to take a look at what type of users might be using it. So in general, a database design is logical design. So deciding on a database schema, this is going to require you to find what a good collection of these relationships are. So we talked a bit about this earlier, but essentially, two types of decisions we might make is a business one and then a computer science one. And this might be something that you talk about with like a stakeholder. So what type of attributes are we going to record in the database? So maybe you're selling stuff. So first name, last name, maybe an ID of the user that's generated, and then credit card information, ways to get that information to, addresses. So these are all business level decisions. Then after you make those decisions, we might be able to say, okay, what types of schemas are we going to create? And how are these attributes going to be distributed among them, right? So maybe each customer shouldn't have their own credit card saved to each one. Maybe it should be linked to a credit card collection table that is linked by an ID to the customer. So and then why do we want to do that? Maybe for security purposes, so that if the customer table might get broken, then we have their credit card saved somewhere else. Okay. We also have this physical design, deciding on the physical layout of the database. And sometimes when you're saying physical here, we might be thinking like tangible, I'm holding the database in a sense, but kind of think of this as the way where it's actually laid out with our arrows and how we're designing it too when we're talking about physical. And so essentially how these files are going to be organized in our system, where would this credit card table be stored, and then how the structure is internally. Okay. So again, you're always going to be having these two competing, not competing, but two ideas that are going to be going at your design, your logical design behind it, and then your physical design. Okay. So let's take a look at an example that we had earlier. So we kind of combined, or we added few new rows here for our database here. So this is similar to what we saw earlier. We have our department name, the building where it is. So this is a new attribute, and then our budget. So let's just say that is there any problem with this design here? If we go ahead and try to update, let's just say physics, I think this example we use, we could also try finance. Let's just say that the budget for finance is going to be updated to 130K here. What will happen is that we need to update it in multiple rows, right? So because we have a finance down here for our department name and up here, what might happen here, let's see if this shows it as well, is that we have many rows we need to update, and that might break integrity. So essentially in our example, we have changed the budget of physics from 70 to 80K maybe. And then again, what happens if that I only update it for my row with Einstein, but I don't update it, I don't update it with my row inside of gold down here. I'm going to break the integrity of our table, right? So we want to make sure that the budgets or ideas, things that we expect to be the same, are kept the same throughout it. Okay. Cool. So a few design approaches to help reduce this is something we saw earlier called the entity relationship model. So this is going to be a domain, again, as I said earlier, entities and relationships. As we saw a bit before, an entity is a thing or an object that is distinguishable from other objects with its own set of attributes, and it's going to be related to some certain other entities that we have. So an ER relationship. There's this other idea that we'll look at a bit later called normalization theory. So formalize what designs are good, test for them, translate a bad into a good design. So essentially, in school, we might have this as well, where if you're trying to get through a project, you'll just get it working. But again, just because it works doesn't mean that it's really a good design, because there's things called case scenarios or edge cases you might think of as well, where you try to think about, okay, what is something that might break my database design in this scenario? And we have to account for that in our design too. Okay, great. So this is a bit of a crazy image, but essentially I wanted to show part of the chapter one book looks at our database internals. And essentially it talks about what type of users will be doing in our entire application. When again, we were thinking of this as a web application or a full stack application, what is going on inside of here after the user uses certain code, how that translates into what is actually managed by the storage manager that we have down here, and then finally into the actual storage of where we're holding this inside of our database. Okay, so we'll go into the internals a little bit later, but down here, we're going to kind of build back up. Our storage manager has a few managers in all of them, different types. So a program module that's going to be an interface between the low-level data stored in the database and the application programs and queries submitted to the system. So this interacts with our OS file manager and is efficient at storing, retrieving, and updating stuff like CRUD operations that we see later. The only issue that this might have is that it might need to have access to certain storage that we have, file organization, and indexing. So what this guy does down here, the storage manager, is that we're not looking at binary data code anymore. We're kind of looking at someone that is a front face in front of it for us here. Okay. Query processing is the one that's above our storage manager inside of our second row here. This is going to be helpful for parsing and translation of our type of non-procedural commands that we have, optimizing some information that we need, and then the evaluation. So if we put in a query, excuse me, such as the one we saw earlier where we said select all from, or select instructor from table instructor where name is equal to Einstein. We're going to parse and translate that into an actual relational algebra expression, which is what we'll look at next week. And then we're going to have an optimizer. We're going to get some stats about the data that we have too. Sorry, my computer keeps jumping around. It's going to start executing that information. It's the engine here that's going to evaluate it. And all we see here is our output from it. So if you've ever used a type of database design system here, let me see if I can run it here. Okay. Sorry about that. So we could see here that is my querying. I'm going to select star from demo. This is just an online SQL type of thing. I'm going to play this one that we have here. We have a couple of them come up, but now I can see that I have these names and information in this kind of dummy information. So essentially, query is up here, and then my query output is what we saw at the bottom down there with all our table information. Okay, cool. This processor, excuse me, the whole processor itself, so not just individual ones, but the whole thing is kind of broken down into these interpreters. And for each of these, the database design language interpreter is going to interpret our statements and then record those into a data dictionary that we might have earlier. The data manipulation language compiler is going to translate these statements into a query language, into a plan that talks in a low level code to our engine that's going to give us a response. And then we have this evaluation. So this is going to essentially do those instructions given to us earlier and then bring them back out for us later so that we can view our output. And then that's kind of what all these three guys do here. Okay. We're going to jump over a little bit here to this idea of transaction management. So I know that there's a lot of vocab being thrown around here, but as we go through the semester, we'll be using these more. So again, you can refer to these slides if you need a refresher on them. But a transaction is going to be a collection of operations that performs a single logical function in the database application. Okay. So what we saw earlier, where I saw select star from demo, that's a transaction there. Okay. So a transaction management component ensures that the database remains in a consistent state despite failures or transaction failures, okay? So system failures, everything goes kaput when the power goes out. Transaction might be more user, so I type my SQL code wrong. We need to make sure that our database is fine after that. Again, concurrency, control manager is going to help out with making sure everything's consistent with our data because we don't want two people to be manipulating data and then seeing different versions of it at different times. Okay, cool. So there's some architecture here. Again, chapter one kind of gives you a broad overview of this information, but it's going to be the architecture of a database system is going to be greatly influenced by what is actually being run on it. Okay, so if this idea of centralized databases, some like one core shared memory that we might have here. This is something like SQLite. So if we have low memory, we're going to need to use more centralized databases. If we have client servers where we have one server kind of working on machines or multiple clients, so a bunch of clients go into one server, that might make us do Postgre and Oracle. If we have two databases running at once where disks are shared, there's a high-end decentralized type of excuse me, a high-end centralized database that we're working with. We might use multiple processor. And then if we have this type of information where my customers are stored in one database, but my credit card information is stored in a different one, we might use Spark or Hive. Okay. So not only do we need to think about our logical and physical schema all the time, but we also need to think about what we're actually going to be able to build our information on, right? So client server is kind of used quite a bit. I would say for our project too, you might have a server running your database and then I'm a client that will join it. So just be aware of these as well. Okay, cool. The last guy at the very top that we kind of looked at here was our users. So naive users, so again, naive users are going to be if people that are just given to software and just need to use it. So when you create your project, I'm going to be a naive user of it somewhat. If you give it to someone else in a different class, they might use it as well. But all they do is kind of interface with the application that's at the top. Application programmers are going to be someone, maybe you as well, that does the full stack development. So they're actually writing in Java or Python or Ruby on Rails, stuff like that to make a functional program. So you're going to write the application program. We have these analysts that might use some things that are used by the application programmers, but might not either. They're going to use our query tools to figure out information to get the data from here. So this is our kind of select star from demo. And then we're going to have admins that are going to use the administration tools. They're kind of the top dogs in this essential thing. Like they have control over everything. And then they are also going to be able to use query tools because they're not only going to be able to look at the data and manipulate it, but they can also add in new tables and modify it as they see fit. Okay. Cool. The last two slides here go over the history of databases. As we saw, is from early 1950s. And then I won't go through all of these just for time's sake, but you can get here that it's modified throughout the years here. The point of all this history, though, is that data is kind of king all the time. So it's important to learn about this as if you understand how these types of systems work, it's very useful in the future. Cool. So again, I think an important thing here, again, is kind of get familiar with your data models, your relationships, and just the vocabulary here, and you should be good to go going forward. Thank you.